Okay, so very sorry about that. There's some technical problems here. So I tried this before. For some reason, something is not working. Anyways, let's get started. I have to improvise here a little bit. So the pen is not working. So I'll maybe use the board or so. Okay, so the first lectures up to now in this course have all dealt with supervised learning. Right? Namely, the problem of learning functional dependencies from data. Right? So given a labeled data set of input-output pairs, x-y pairs, learn a function mapping x to y. Okay, so what we want to start talking about today is what's called unsupervised learning, which is basically learning without labels. Right? So it means there's no y's. Or we have to figure out what are the y's. Okay, so now unsupervised learning refers to a family of different techniques, just as supervised learning does. It's widely used when sort of trying to find patterns in the data without knowing necessarily a priori what those patterns are. Right? It's very useful for exploratory data analysis, right? For visualization of data sets, etc. Right? So it's a whole family of techniques. Now, in supervised learning, the two canonical supervised learning tasks that we had been talking about, essentially all semester so far, was regression and classification. And so there's two analog canonical unsupervised learning problems, and these are clustering and dimension reduction, which you can view as basically as some sort of unsupervised analogs of classification and regression. Okay, so clustering is some sort of unsupervised analog of classification, and dimension reduction is some sort of unsupervised analog of regression. Okay, so we'll start now actually talking about clustering first, and then we'll move on to discuss dimension reduction. And again, we'll parallel what we've discussed, what we've done in the context of supervised learning, right? In supervised learning, we started with the simplest models, right? We started with least squares regression and then sort of build concepts around that. And we'll again start with very simple but important notions of clustering and build around those later. Okay, so clustering. So what is clustering? So the general goal in clustering is to somehow, given a collection of data points, group them somehow, right? Group them into clusters of points with the general preference that somehow similar points end up in the same cluster and dissimilar points don't end up in the same cluster. That's sort of the high-level idea. Okay, so discovering group structure in data. Okay, and now of course, in order to make this more precise, we again have to talk about representation of data, right? So how do we represent our individual data points, right? And then we'll have to specify preferences, right, for different groupings or partitions, etc. And then find out ways of solving those, right? Paralleling what we had discussed in the context of supervised learning. Okay, so now what we'll again do as we continue, basically continuing as what we have done in earlier lectures, is we'll assume points, basically data points, are vectors in some high-dimensional space. Okay, so it'd be great if I could actually visualize my slides. I don't really know what's happening here. Try one more thing. Okay, keep fingers crossed. Good. So, okay. So representing points as vectors in some high-dimensional space, right? Our feature vector representation. This is the default representation we'll be talking about. But of course, one can have other representations as well, as we've had touched in the context of supervised learning as well. So in particular, right, you can talk about clustering under some notion of similarity, right, or metrics, etc., that you would define between pairs of data points. And that's mostly closely related to what we've discussed here in the context of kernels, right, where you would view kernels as a similarity function. And we were talking about clustering in the context of kernels in a little while. Okay. Now, one related notion that I want to briefly mention here, so one of the use cases of clustering and clustering techniques also relates to things like anomaly detection, outlier detection, right? Because typically what you would want to do is you would somehow discover groups in your data, right? That sort of describes where the bulk of your data set lies. And that's very useful if you can describe this well, because you can detect if there are some points that don't fit well with existing group structure, right? And that's typically a sign of outliers or anomalies, etc. We'll talk a bit more about that. Okay, so here's sort of a simple kind of clustering problem, right? So a very concrete two-dimensional data set. So this picture here, so that's a famous geyser in Yellowstone National Park, Old Faithful. It's called that way because there's a very strong, first of all, regularity and outbursts and eruptions, and also very strong regularity in the behavior of that geyser. Okay, and so here's some data that has been collected over the years. And so there's two features, x1 and x2. So x1, the x-axis, is the duration of an eruption in minutes, and the y-axis is the time between eruption in minutes. Okay, and so there's a very strong linear correlation, as you can see here, right? And also you can see that there's sort of two clusters of points. Okay, now, or at least it looks like there's two clusters of points. I can ask you how many clusters there are, and that's a topic that will be coming later, right? But sort of maybe one can argue that there's sort of two large groups of points, right, and some points spread around here. Okay, good. So that's one concrete example. Of course, there's lots and lots and lots of applications of clustering, right? It's a ubiquitous task. You might want to cluster documents, right, based on the words they contain, or images based on some sort of feature representation of the images. You might cluster patients, right, according to certain medical features that you observe, right, etc. So there's lots and lots of applications of clustering tasks, right? And there's a bunch of general families of approaches towards clustering. On this slide, I want to give you a bit of a high-level idea, the sort of cluster approaches of clustering. And then we'll focus on one of those and discuss it and explain it in more detail, as we've done in the context of supervised learning. Okay, and so the three general clusters of clustering methods are hierarchical, partitional, and model-based clustering approaches. Okay, so hierarchical clustering is basically sort of roughly works as follows. So you have your data set, and let me actually try to write a little bit if I have some chalk. Okay, so sorry for improvising a little bit. Right, so basically, sort of you have your data set, right? You have your points here, right? A bunch of clusters of points. And now what you would do is you would basically form a tree, right? Sort of group pairs of points together. So you might always, for example, merge together the two clusters that you've already merged that are as close as possible together, right? So you maybe merge those points, then you might merge those two clusters, you might merge those two clusters, in the end you might merge those clusters. So that gives you a tree that connects all the points of your data set, like a spanning tree of all the points in your data set. That's not yet a clustering, so how do you get a clustering out of it? Well, you cut the tree. You chop it at some level, right? And so here, in the end, you would end up with these two types of clusters, okay? So that's a family of clustering-based techniques. Now, there's lots of different flavors and variants of this approach, right? You have to figure out how do you measure similarity between points, how do you measure similarity between clusters, right? And the strategies of growing this tree, right? And deciding where to cut this tree, etc. Okay? But that's sort of one large family of clustering approaches that you should know about that we won't discuss more in this class. Okay? Hierarchical clustering is something that is very commonly done. Okay, so the next family of clustering approaches are called partitioning approaches, or partitional clustering approaches. And they basically take this notion, this definition of a clustering as a partition, right? You have a data set, you partition it into disjoint sets of points, right? And now you somehow define a cost function over those partitions and optimize that resulting cost function. Okay, and so one way to sort of think about this, so suppose you have a two-dimensional setting here, right? So this is x1, this is x2, okay? And you have a bunch of points, maybe like those, okay? And now what you would do, typically, is you would form some sort of tree, look at some sort of neighborhood structure, maybe connecting up all nearest neighbors in some way or the other. Maybe you draw an edge, right, between the point and its nearest neighbor, or sort of its k-nearest neighbors, or something like this. You might attach a weight to the edge or not. Again, there's lots of different flavors of this algorithm. And now you get the graph, and you cut that graph. Okay, you might find a cut in that graph. So for example, you could look at as a cost of a partition the number of edges that cross between these different nodes. Okay, so that yields a graph cut problem, right? So, and now of course, again, there's lots of different things you have to specialize, right? How do you make up that graph? What makes up an edge between 2 points, right? What's the weight of the edge? And how do you quantify the cost of a partition? Okay, so that's an example of a partitional, right? Sort of the high-level idea behind these partitional approaches. I also will not discuss these more here. Okay, but these are two main families of clustering approaches, these hierarchical clustering approaches and partitional approaches. And so what we rather will focus on here are what one typically calls model-based approaches, where one tries to come up explicitly with a model of a cluster and then try to learn the parameters of those of this model. Okay, so these are the classes of techniques that's most similar to those that we've discussed in the context of supervised learning. Those yield optimization algorithms that we can then try to solve. Okay, and so there's a bunch of examples of such approaches. And so the one that we'll start with is sort of clustering 101. That's the k-means algorithm. And that's sort of the perceptron, right, for classification, or maybe least squares linear regression for regression. We'll discuss some of the issues that come up here, and then we'll generalize these ideas later. Okay, so that's the idea. There's a lot more to say in general about clustering and unsupervised learning in particular in some of the more advanced classes. Okay, so what's k-means? So here's a data set with a bunch of clusters. I don't know how many. Now, suppose there's 3 clusters, right? We'd like to discover those. So what's the idea? Is we want to model them. So how are we going to model those clusters? We're going to model those clusters via their center, the centroid. Okay, so we represent each cluster by a single point. And this is not necessarily a data point. There's variants of this kind of problem where these cluster centers is actually a data point, but here it's not necessarily. Okay, so each cluster is represented by a single point. And now this point induces a clustering, okay, via the distances. Okay, so what you would do is you would basically look at the Voronoi partition of the space that's induced by the set of points. So what's this Voronoi partition? So this Voronoi partition is basically a partition of the space according to the distance. Right, so let's just draw this here. Okay, so basically if these are our points, our cluster centers, right, then what we would do is we would look at basically what are the set of points that are for which each of these cluster centers is the closest. Okay, so for example, if you just were to take those two, you're going to get this line here, right? So everything on that line is closer to this one than here, right? Again, here we're going to get this line. Again, here we're going to get this line. And now these are going to meet up somewhere, right? Right? So, okay. Maybe I've, whatever. So suppose they meet here, right? Okay. So basically, so in general, right? So it's basically induces a partition, right? Such that these points over here are essentially the points for which this point mu1, right? The center of this point is the closest. So this is the set of all x's such that 1, so if this is cluster 1, mu1, mu2, mu3, right? The set of x's such that the number 1 is in the argmin over j in 1, 2, and 3 of the distance, right, of this point x minus mu I, according to the Euclidean norm. Okay, so this basically gives it this resulting partition, right? So the cluster centers determine the resulting partition. Okay, that means once you have those cluster centers, they tell us the partition. Okay, we parameterize the partition via these points, via these centroids. Okay, And now the question is, what kind of partition do we want? And that means we now have to specify some sort of optimization problem, right, that tells us preferences over partitions. Okay? And so the preference that we're going to look at is basically what's called the quantization error. So we're going to define a cost function, an empirical risk, right, similar to that we've discussed in the context of supervised learning, R hat, that now takes as inputs candidate cluster centers mu, k of them, if you have k clusters, right, mu1 up to mu k, each of them is a vector in Rd, right, in the dimension of our input feature space, right, and this cost function depends on this joint selection of these k cluster centers. For now, let's assume that k is a given constant, right? We know we're going to look for, say, 3 clusters, right, and we just optimize over the parameters of those 3 cluster centers. Okay, so we're going to solve an optimization problem over 3 d-dimensional vectors, mu1, mu2, mu3. Okay, in general, mu k. And now the cost function that we use, right, the empirical risk, is just the sum over data points, right, the same form that we've discussed all along. And the contribution of each point, the loss incurred by a given point, right, is simply the squared Euclidean distance of that point to its closest center. That's the k-means loss function. Okay, right? So we've talked about loss functions all through the semester. That's a new loss function, right? It's the k-means loss function, right? So the k-means loss function takes the data point x and uses it to evaluate the loss associated with the candidate set of cluster centers mu, mu1 through mu k, right? And it evaluates to the smallest squared Euclidean distance among all those points. Okay, so now that's a well-defined objective function, and we can try to solve it, right? We can try to optimize it. We can now try to ask, how can we get our estimator, mu hat, right, as the set of centers, k centers, that minimize this cost function. Right? That looks very, very similar to the kind of problems we've talked about, right? In fact, looks very similar even to the least squares problem that we had talked about, right? Least squares regression. Okay? Now, unfortunately, similar to what we've discussed in the context of neural nets, this is not a nice optimization problem, right? It's a non-convex optimization problem. So in general, even though we might be able to use gradient methods to optimize it, in general, we'll get stuck in local optima. In fact, it's an NP-hard optimization problem, right? So it's a pretty simple optimization problem, but can be shown to be NP-hard. Okay, so we'll generally not look for optimal solutions here, right? But we'll look for approximations. And the maybe most famous one, sort of what's often also called the k-means algorithm. But again, I want to keep in mind here, right? Want us to keep in mind that we always distinguish between the problem we want to solve and an algorithm for solving that problem, right? So this is an algorithm called Lloyd's heuristic, but oftentimes in the literature you might see it referred to as the k-means algorithm, right? Because it's sort of the standard algorithm that's used there, okay? And so the way it works is it starts with an initial guess, right? And of course, it's a non-convex problem, right? The same issue that we encountered in context of neural nets, right? You can't just walk downhill, so the starting point matters, so we'll have to worry about initialization, right? But let's do this in a few slides from now, right? You initialize somehow, and then you iteratively refine your solution. And how does this refinement work? So the refinement works as follows. So every round you have your current set of centers that you maintain, right? Mu j of mu of t minus 1, right? Here the superscript is the iteration number, the subscript is the cluster index. Okay? And so what we're going to do is we use our current set of centers in order to infer the class membership, right? That means we basically use this Voronoi partition to label our data points. Right? So we're going to look for each point, which cell does it fall into, and assign its label. So basically apply nearest neighbor classification with respect to the cluster centers mu. Okay? So basically each data point we'll classify according to which cluster center is it closest to. And we'll call that index CI for the ith data point, right? It's the argmin over all j clusters of the one that's closest. And then what we're going to do is we're going to update the centers simply as the mean of all the points that we've classified according to that cluster. Okay, so we'll collect all points that we've, say, assigned to cluster 1, and we just look at its empirical average. Okay, so nj here is just the number of points we've assigned to cluster j. Okay, so that's basically the algorithm. And here's an illustration of it on this Geyser data set, right, with a sort of dimensionalization, right? You start with mu1 and mu2 in red and blue, right? And so we first would classify, right, do the nearest neighbor classification. So you look at the Voronoi partition, right? Now we look at, for each point, is it closer to the red or blue cluster, and color these points accordingly, right? And then what we would do is we would update these points to the respective means of the colored points, right? So here, once we have all these red points, we would now just compute the mean of all the red points and update the red cluster center to be that mean, and we would do the same thing for the blue set of points. Okay, so we do this update, and then we repeat, right? So now this is our next guess for our cluster centers. We again look at the new Voronoi partition, relabel the points, right? And proceed, and after very few iterations, we're done. Okay, so that's basically the algorithm. So it's really simple. Note that this is not the gradient-based algorithm, right? So it doesn't sort of do gradient descent on the cost function. Okay? That said, yeah?
You say the number of clusters before you start?
Yeah, k is a fixed constant, okay? 2. Okay, so and we'll worry about what is k in a moment. Okay, so that's clearly a question, right, that we need to think about. Okay, any questions about the algorithm? It's really super simple. Yes?
Any way to verify if the clustering is like good or not?
Yeah, so very good question. So no. Okay, so in general, okay, so we'll get back to that. But in general, model selection in unsupervised learning is very difficult. But we'll talk more about that. Yes?
How should the result depend on the condition?
Yeah, so absolutely it does, and we'll see examples. Okay? Keep that question in mind. Other questions on the algorithm? Okay, so what can you say about this algorithm? Well, it solves k-means in polynomial time. Of course not, right? That would show that p equals np. So it'll in general have some problems. So what are the problems? So first of all, what's good about the algorithm? So the algorithm monotonically decreases the objective function. So even though it's not a gradient-based algorithm, that sort of walks, right? So in the direction of all cluster centers that decrease the cost the most, it monotonically decreases the cost. So if you compare our hat of mu t with our hat of mu t plus 1, then ladder quantity is always at most as the previous quantity, right? And in fact, whenever there's a change in assignment, it strictly decreases. So I can show that as long as 2 points change the assignments, the cost actually strictly decreases. And that guarantees convergence of the algorithm, right? Because the cost is lower bounded by 0, it can only decrease, right? And can only decrease when there's actually a change in the clustering, right? And there's at most exponentially many clusterings, right? So at least it must converge in finite time. Okay? Now what does it converge to? In general, only a local optimum, right? So it only converges to a local optimum, and the complexity per iteration, which I'd like to annotate here, is basically just, we can try to work it out. So what is the work it does per iteration? So what does it have to do, right? So there's 2 steps, right? There's the classification step, right, where we infer the class labels, these hidden variables set I, for each data point, right? These latent class assignments, right? Set I. And that's, how does it work? Well, for each point, so there's some O of n here, right? You have to look at, for all the clusters, something that's order k, compare the distance, order d, right? So there's some work that's basically order n times k times d, right? That you have to do in order to figure out what's the closest point, right? to the current data point, right? What's the closest center to the current data point? Okay, and then you have to update the cluster centers. So much work is updating the cluster centers. Well, that's basically just computing the mean of all the points in the data set. So that's just n times d. Okay, so really the work is dominated by figuring out the nearest neighbors, right? The nearest clusters to each point. So it's order n times k times d per iteration. And of course, the question is, what's the number of iterations? And so it turns out you can actually cook up data sets that make this algorithm take exponentially many steps to converge. Okay, so not only does it can get stuck in local optima, you can even make it take exponentially many steps to get there. Okay, you have to try really hard though. Okay, so that construction is actually pretty complicated. But you can make it take exponentially many steps even in the plane. So that's a paper not a bunch of years back. Okay, good. So what about, so I mentioned, right, it doesn't always find global optima, right? And here's an example where it doesn't, right? So there's 3 clusters. That's the optimal solution. And here, that's a bad solution, right? So, and basically what happens here, if you have those cluster centers, right, then what happens is if you take this partition, the Voronoi partition associated with these 3 points, right, then the mean stays the same. Right, so here basically this point is the mean of all those points here, so it wouldn't change. That's the mean of all those points, so it wouldn't change, and that's the mean of those points, so it wouldn't change. Right, so it means that with these cluster centers, right, it wouldn't do any updates anymore, so it would terminate. Right, so that's an example of a local optimum. Okay, and that does depend on the initialization, of course. Right, so if you happen to initialize it as on the right, well, then obviously it's not going to do anything, right? If you happen to initialize it on the left, it's going to work, right? And of course, you don't have to be as close to the optimal clustering. But initialization does matter. Okay? Good. So let's talk about some of the issues. So that's basically the k-means problem, right? And the sort of standard algorithm for solving the k-means problem, right? Lloyd's heuristic. Now, what are some of the issues? Well, so to summarize, so there's generally the algorithm only converges to local optima. So the performance does depend on initialization. The number of iterations can be exponential, even in the plane, but that basically never happens really in practice. So that's really more of a theoretical issue. Now, determining the number of clusters, we haven't said anything yet, and in general, that's a difficult problem. So we'll talk a bit more about that. And so the other issue, and we'll see some examples of this, is that k-means as a problem is not very well suited to model clusters of arbitrary shapes. Okay, so it's very well suited to sort of capture sort of circular shapes, right? So essentially circular clusters, right? That where sort of each circle roughly has the same diameter, right? But if you have more complex shapes of clusters, it may fail. Okay? And so we'll see some of those issues and go through some of them in some more detail. And so the first one is this initialization business, right? How do we initialize k-means to do something sensible? And now, we said already initialization matters, right? So what choices do we have, right? So the one sort of a sensible choice one could sort of think about is some sort of random initialization, right? But now you already have to talk about how you randomly initialize, right? You sort of put the points randomly in the plane, but then you really already need to sort of know where the data lies. The other thing you could do is you could sort of pick data points itself as initial cluster centers uniformly at random, right? And that's actually sometimes done, right? So basically initializing each cluster center, mu I, as a randomly chosen data point. Okay, that's sort of the simplest initialization that often does okay. But it can have problems, and we'll see what some of the problems with this are. Okay, and so turns out there's better things of what one can do. And so I'll tell you about one way to initialize That's essentially the default. It's a super simple algorithm that's actually extremely effective. And that's called k-means++, and it's a really nice algorithm that I want to just tell you about. So, but before we do that, let's see what's the issue with random seeding. Okay, so seeding is the random initialization, right? So what I meant, random seeding, what's typically meant is you basically pick data points as cluster centers. Does anyone see sort of what could go wrong if you initialize cluster centers just as randomly chosen data points? Does anyone have an intuition of what might be the problem? Cluster. Right, exactly. So if you just draw the points uniformly at random, then the issue is that if you have clusters of different sizes, chances are that you're only going to sample points of that one big cluster. Okay? And so what's often really important is that somehow you initialize not too far away, right, from all of the clusters in your data. Okay, so that's really the problem with just uniformly random seeding. Okay, so basically if this is your data set, right? So there's notably this one big cluster over here, right? So if you were to now pick 3 random data points as your cluster centers, chances are you'll pick 2 or 3 from this large cluster, okay? And then it might be difficult for the algorithm to figure out that there's yet another cluster over there somewhere. Okay, that's sort of the intuition. Okay, so right, you might oversample large clusters and you might undersample small clusters. That's basically the problem of just randomly initializing. Okay, so now what does k-means++ do? So it basically works as follows. So the algorithm works as follows. So what you're going to do is initially so we pick the first data point uniformly at random from your data points. Okay, so we would say we draw I1. It's the index of the data point that will be our first guess for the first cluster center. We just draw this uniformly from all our data points, right? And so now so here in this example, right, where there's big clusters and there's lots of smaller clusters, most likely that's going to be in our big cluster. Now what we want to do is to avoid only sampling points from this big cluster. We somehow would like to sample points that are far away. That's sort of the intuition, right? That's how you could fix just sampling points from a large cluster. So the first heuristic that you might think about is what's sometimes called farthest first. You could say, I have my points, and now I'm just going to find the point that's furthest away from the point that I've had so far. Anyone see any issues with this? If you just look at the furthest point, so the issue with just picking the furthest point is that there's, yeah? Outliers, exactly, right? So there might be some points very far away that are isolated, don't really make up separate clusters, right? But these tend to be far away, so you're going to pick those, right? So this furthest away will be prone to this issue, okay? So now what you want to do is you somehow want to balance sampling from clusters that are sort of well represented, where there's a bunch of points, but also that are far away from what you have. And that's what k-means++ solves, okay? And the idea is basically that we're going to randomly sample, but not uniformly, but non-uniformly, according to the distance to all the points you have so far. Okay, so we'll start with the first point, and we'll just be set mu1 is basically xi1, so first data point, right? And now, then what we're going to do is we're going to iterate, so from j equals 2 to k, we would draw ij. We basically with proportional to, so there's a normalization constant here, but otherwise just the distance to the points that you've sampled so far, okay? So here, let me write d of so equals I, the distance of this point xi from centers mu1 up to j minus 1. And so what is this distance squared, right? And this is here just the min over j overall okay, let me write min over L, 1 less than L less than j minus 1 of the distance of xi minus mu L to norm. Okay, so this is just the Euclidean distance of the ith point xi in your data set to all the cluster centers that you've already selected so far. Okay, and now what you're going to do is you're going to basically sample the point proportional to that squared distance. Okay, so here. Oh, so this is 1 less than or equal to L. So this is an L, right? Just an index, right? So this is basically the minimum, the closest distance between xi and any of the centers that you've picked so far. Okay, so this is xi minus mu L, the Euclidean distance. Okay, and then we'll just set mu j to be xi j. Okay, so that's basically the algorithm. And here, what we haven't said yet is this normalizer. So set is just the sum over I equals 1 through n of, right, to make the whole thing normalize, right? xi comma mu 1 up to j minus 1 squared. Okay? So now, what does this do? Yes? Is that typo?
With this algorithm, the outliers will still have the highest probabilities, but you're going to sample the other points.
That's the issue. That's exactly the point, right? That's exactly the key idea, right? So the idea is basically now here you're going to sample points that are far away more likely, everything else being equal, than points closer by. So it means that outliers will have a higher probability, right, than points that are closer by. But the point is that if there's some cluster with a lot of points you haven't represented yet that's closer by, each of the points in that cluster has a good chance of being sampled. That's the key idea. That's what makes this algorithm work. Okay? And so here's an illustration of this. So here's basically an illustration of this algorithm in practice, right? So you start with uniform probabilities, uniform weights for all the points. Okay? And now what we would do is we would draw one of the points, maybe from the big cluster. And now we're going to compute the probabilities according to this formula that we've discussed here, right? So you would go through all the points, compute the closest distance to any points you have, so any centers you have so far, and square that, renormalize. So that's going to give the probability of sampling each of these points. And here the diameter of these circles is representing the probability of being sampled, right? So the weights is sort of the probability of being sampled. So the idea is once you've picked this point, all of these points close by are going to be unlikely to be sampled, and the points in these clusters here are going to be much more likely to be sampled. And now we draw one of the points according to this non-uniform distribution, right? Maybe sample this point up here, right? And then we recalculate the weights. Okay, so we now would figure out, right, that these are the only points that are far away from all the centers that we've picked so far, so these are the only points left that have a large weight. And now we sample the last point. Okay, so that's basically the algorithm. Right, it's randomly sampling, but clever random sampling, right? Non-uniform random sampling. And this algorithm just works extremely well. Okay, if you have a data set that's sort of where K-means is sort of a sensible model, it'll typically give you a good solution. Yes?
I do understand how to deal with outliers.
So yes, sure. So basically the way it deals with outliers, right, is that points that are far away will have a higher probability of being sampled, but they're alone, right? So there's points closer that have a smaller distance, but there's lots of them, so you're going to sample them rather. That's the idea. Okay? That's a really nice idea. And this is basically the default standard initialization, right? So what you would do in practice, right, is you would use k-means ++ to initialize, and then you would run, say, Lloyd's heuristic, or you would actually run stochastic gradient descent on the k-means cost function, which you can also do, and it'll give you a good solution. Okay, so that's basically the standard algorithm. What this does not tell you yet is how to pick k. So what I would suggest is that we'll take the break now, and then after the break, we'll talk more about model selection for clustering, and then continue the discussion. Okay, so let's continue. So we've talked about k-means clustering as our simplest approach towards clustering, right? We've talked about the k-means optimization problem, namely finding the cluster centers that minimize the quantization error, which is, in this case, our empirical risk. We've talked about a new algorithm, right, for solving that optimization problem, namely Lloyd's heuristic. That's a bit different from the kinds of algorithms we've talked about before, right? Not a gradient-based algorithm. And we'll see other examples of similar algorithms later on in this class. And we've talked about this issue of initialization. And talked about the k-means ++ algorithm, which is a really elegant, simple, randomized algorithm that not only works extremely well in practice, at least on problems where k-means is sort of the right clustering technique. It also has some nice theoretical guarantees that I haven't mentioned. So it's an approximation algorithm. You can prove that even immediately after initialization, once you've run k-means ++, then the resulting solution is actually already very good. So you can show it's, if you compare it against the optimal quantization error, so the cost, the minimal empirical risk that you can achieve, it's only a logarithmic factor of a, so order log k of a in terms of the quantization error. Okay, so it has a nice theoretical justification as well. Okay, what we haven't talked about yet is where does k come from, right? And that relates to this issue of model selection, right? And we've discussed this extensively in the context of supervised learning, right? We talked about what kind of features do we want to use, right? Do we want to fit polynomials of degree 3 or polynomials of degree 5, right? And so how complex models do we want to fit our data, right? And in some sense, clustering, you can view through a similar lens, right? You can ask how complex of a model do I want to fit to my data, right? Am I going to sort of look for 3 cluster centers or 5 cluster centers? Okay. Now, one big issue is that in supervised learning, you do have a clear task, right? You do want to learn this functional dependence, right, between x and y. You want to learn a mapping x to y, right? And whatever model lets you do a better job at that prediction is the better one, right? And now basically you have a clear objective that you can validate and optimize for, right? That was our strategy in the context of supervised learning that led us to discuss cross-validation and these sort of things, right? Now the problem is in unsupervised learning, you don't really know kind of what is the task that you want to solve. I mean, I'll give you a bit of an idea of how you can view what kind of task you might solve with unsupervised learning a bit later. But it's sort of a much less well-defined problem, right? What is really a cluster? Okay, and so that makes model selection a lot harder right? A lot less well-defined and a lot more problematic. And this choice of K is sort of the simplest example of this. How many clusters do I find, right? But similar issues you have in, I mean, suppose you now have different clustering algorithms, right? How do you choose which of the clustering algorithms you want to pick? They might not even optimize the same objective function and so on. Okay, so model selection is really, really hard in unsupervised learning. And there's no really good answer. So there's a bunch of different heuristic quality measures for sort of giving practical recipes on how to pick K, say in K-means and related tasks. But in general, it's a very difficult question. I mean, there's some ideas that are being explored in the literature, but it's not really a problem that everyone agrees on. Okay, so one, in terms of one of the heuristics for determining K, is basically as follows. So if you think about this problem of clustering as some sort of resource allocation, right? You sort of plant a cluster center, and now this is responsible to a subset of points in your data set. Right? You can now think about sort of a cost of planting such a center, and you can sort of think about the diminishing returns you get by planting additional cluster centers. Right? So if you plant more cluster centers, sort of fewer points have to go a large distance to their closest cluster center. Okay, it's actually related to ideas from facility location and operations research and so on. And if you take that perspective, you can sort of think about diminishing returns, right, in the cost that you would incur, right? And this, for example, in the improvement in objective function. So here, what this plot basically shows is a data set, right, with a bunch of clusters. I don't know how many clusters there are. Do you want to take a vote? So think about how many clusters would you see here? Is there anyone who says there's one cluster? There's two clusters? Yeah, what? 4, okay, so 4 clusters. Yeah, okay, so it seems like, okay, 5, 6, 1,000? Okay, good, so I can argue about this, right? But essentially what this plot here shows is as I increase K, and I sort of do a good job at solving the resulting K-means problem, meaning, right, running K-means plus and doing maybe multiple restarts and really not get stuck in local optima, I get sort of a nice curve that looks like this, right? That's the cost function if I use one cluster. By the way, what's the optimal K-means solution for one cluster? The mean, right? So the one mean solution is the mean of the data, okay? So it's easy to see, right? So it's basically the mean, right? And there's now 2 clusters, 3 clusters, 4, 5, and so on, right? And what you see is that this curve sort of has this kink here, right? So it's basically sort of a sharper angle, right? And sort of it looks like an elbow, okay? And so sometimes this heuristic is called the elbow method. So you would look at the elbow of this curve, right? And sort of see that's the best value of K. Okay? So that's sort of one heuristic that's sometimes used to determine the value of K, right? Now you can view this through the lens of regularization, right? So what you can say is, well, what if I have my cost and now I actually add a penalty, right, that quantifies my model complexity? Right? So for example, what you could say is I could say I have some cost for using more clusters, right? I not just have some of the cost that I incur by having to compress my data, right, through quantization, but I also have a cost for opening up new cluster centers, right? So I could, for example, do something like right? I could take as my risk, right, r hat of mu, right, to be the sum over I equals 1 through n of the distance of xi to mu squared, right, plus lambda times k, right? And now mu does depend on k, right? And I could say, let me optimize, right, over k, and then inside I optimize over mu1 up to k, right? So that's sort of how you can think about regularization in the context of k-means. And that's how I determine this red curve here, right? So I pick some value of lambda, right? And then I basically plot this curve, right? So this blue curve is the one from the previous slide, right? It's basically just how does my quantization error decrease as I use more and more clusters? And the red curve is how does this cost function, this regularized cost function, change, right? And that's initially going to go down because these clusters are really worth it. They represent lots of points well. And then I have to pay additional costs, right? That might only improve the distances a little bit. That's sort of the idea, right? And so this is really the same as this elbow method, right? As we had in the previous slide. It's just one way of interpreting this. But now, of course, the question is, how do I pick lambda? Right? Instead of picking k, and I have to pick lambda. And normally in supervised learning, I would ask you, right, what to do, right? Cross-validation. But it turns out this actually doesn't really work here that well. Okay, so for example, what happens if you really do k-means and you sort of compare performance on training and test error, you actually oftentimes really get a very strong dependence of the training and the test error. Right, so it's very hard to detect overfitting. Yes? So in this case, I would draw training points for training and test points for testing. The same thing. So this is a validation loss, right? So I would here take my so independent points drawn from the same distribution, right? These sort of 4 Gaussians, right? In the previous training points, exactly, and I measure the performance on the test set, right? That's how I evaluate the same thing we've done in supervised learning, right? That I could do, right? I could measure sort of my generalization error, my prediction error by looking at the quantization error on test examples. Okay, but it doesn't give you a very good signal for k-means. Okay? So unfortunately here, really cross-validation is not the right answer, at least not looking at this empirical risk. Okay, so it's really a bit of a problem, right? So basically, this is sort of maybe the most sensible thing to do, right? To include some sort of penalty, right? And we'll talk more in later lectures in this course about sort of probabilistic interpretations that'll correspond to doing something like a certain prior in certain models. So you can give some sort of justification for this kind of procedure, but in general, it's difficult. Okay, now that's one of the issues, right, with k-means, namely how to determine k, right? The next question is, how do the solutions actually look like for different data sets, right? So here's a simple example of this data set. So let's play the game again. So how many clusters are here? So who says there's 1 cluster? Who says there's 2 clusters? Okay, so good. So how about 3 clusters? How about 4? How about 1,000? Again, no? Okay, so I don't know, right? Maybe it's 2, right? I sort of generated it from from 2 clusters. But basically, what happens if I run k-means on this? Any guesses? It'll solve this problem. So this is actually an optimal solution. All right, and the resulting partition, right? It would say there's 2 clusters, one here, and this sort of represents all those, this represents all those. Okay, and so that's sort of not so good, right? So it's not very well suited, right, to capture clusters of arbitrary shapes, right? Because here really the assignment of points is purely based on the distance of points, right? So one of the issues here is that one of these clusters is much more elongated than the other cluster, right? So maybe you should measure distance for one of these clusters using a different metric than for the other cluster. And later on, we'll be talking about using more complex models for the clusters that will deal with these issues, right? That's sort of one of the issues when applying k-means to this kind of data set. Okay, so that's basically the problem. Let me actually show a quick demo here to get a bit more intuition of sort of what happens. So this is one of the notebooks I put up. This is the data set. So how many clusters are there? Okay, so I'm not going to do this again. So we can basically use different algorithms for fitting. So I'm just going to use k-means initialized with k-means ++. What? Oh, no. Why? Yeah. Okay. I'm a bit worried that if I switch now. Okay, so I think it should be fine. Try this. No. Aha, but now at least now I can show this. Okay, good. So here's the demo. Good. So how many clusters are here, right? So 3, hopefully. So let's see. I'm going to run k-means for different values of k. So here's 2, right? So now it assigns those 2 clusters, right, to 1. And this is a separate one. And now this is what happens if I do 3. So what's going to happen if I go to 4? Any guesses?
The lower left one, and then second, top right, 2 and half.
The top right. Okay, so one of them, right? So, okay, good. Let's keep going. All right. So it'll keep splitting those clusters, right? And now I can keep going more. Right? I'll always pick one of them and keep refining it more and more. Okay. So that's basically what's gonna happen. Okay. And so you can change the data set. So here's one. Okay. So circles one, right? So k-means with 2 clusters going to do this, right? So by the way, will it ever be able, right? So how many clusters are here? Okay. Who says 1? 1? Okay. Who says 2? Okay. 3? No. Okay. So basically, right. So arguably there's 2 clusters, right? 2 sort of densely connected regions somehow, right? But k-means thinks there's, right, doesn't know what to do with this, right? So one of the issues, of course, if you just plug in 2 clusters, then the Voronoi partition is always going to be, so there's always going to be a line, right, between these 2 clusters, right? So it must have a linear decision boundary, right? So with 2 clusters, there's no way it's going to be able to capture this kind of geometry here, right? If I use 3, it's going to split this up, right, in sort of strange ways. Okay, so k-means is clearly not a good algorithm for this kind of data set. Okay, so some others, right? Similarly here, right? How many clusters? Okay, so 2 maybe. And so if I split this here, right? Again, this is sort of the best line it would do. That's sort of decent, but still doesn't really capture these clusters too well. Right? With more, 3, 4, 5, and so on. Okay, so k-means maybe not so good. How about this? How many clusters? Okay, so right, you can also again keep increasing this, right, and sort of nicely tiles this, right, into a roughly uniform. You can sort of see a preference, right, of the k-means objective function in terms of the clusters it will produce. Okay, so here's this kind of thing, right? So yeah, I talked about before, right? 2 clusters, 3, right? It's not going to do too well. Okay, so k-means, at least in the most basic variant, right? Better give it data that looks like this. Okay, so at least if you really wanted to describe clusters well, you actually have to have nice isolated spherical clusters. Otherwise, k-means is going to have a hard time. Okay, so be careful with just running k-means and interpreting the resulting clusters really as clusters, nicely connected dense regions. Very rarely it's going to work. Now, that doesn't mean k-means is not a very, very useful algorithm. Okay, so k-means actually has a lot of use, right? So in particular, you can fix these kind of problems. So I'll later on talk about changing the representation of the data. It's sort of the same as linear classification, right? You can fit highly nonlinear decision boundaries if you use the right kind of representations. And we can actually, let me just show you this briefly to not make you completely disappointed in k-means. So this one here, right? Oops. So let me, for example, show this data set. Right? So here, for example, that's now a k-means solution, but just in a different space that we'll work towards later, right? Or here, right? So you can actually deal with these sort of things. Okay, so not here, right? But there's maybe not so much to argue. Okay, so this, I don't think it models super well. Well, okay, sort of. Still better, right? So you can fix it if you go to the right representation of the data. Okay? It's just a sort of a point of caution, right? So if you just apply k-means on sort of the most naive feature representation, you're going to get garbage. Don't do it, right? Unless you actually want to use it for other reasons. So it turns out, so what we've seen, right? So for example, when using k-means, even on problems like this, right? This kind of nice tiling, right, of the space can actually be very useful. So for example, what often can be a good idea is to run things like k-means even on sort of naive data representations with a very large number of k, and then essentially use the resulting discrete label as a feature of your data. That can actually be very useful for feature induction, and is actually used quite a bit. So there's sort of lots of uses of k-means, but don't just naively apply it to this basic data representation, right? That's maybe the lesson learned here. Okay, so now let me see if I can actually recover my slide. No. Oh, oof, no. Shoot. Okay, so sort of what we had discussed. Oops. Okay, good. So this is basically this list of issues with k-means, right, to sort of summarize our state of affairs. We said one issue is generally only converges to local optima. That's not, right, not really so much of an issue with the right initialization, right, k-means ++. It can in principle take a lot of iterations, right, not really an issue in practice, right, with the right initialization. So the first two are basically non-issues, right? The third one is sort of this can't well model clusters of arbitrary shapes. That is an issue if you just apply it naively, right? But you can fix it with going to sort of proper representations, and we'll talk more about those later. The big question really in practice, and that's really not well resolved, is how to validate a model. Okay, I don't know what to do. Okay. I'll turn around my laptop, right? So I'll take a look here. Why don't you call them here, right? So, okay. Good. So that's basically right, a summary of k-means up to now, right? You need to understand what's the k-means optimization problem, how do you solve it in practice, right? Including this initialization with k-means ++. We've talked about these heuristic ideas, right, for choosing k via regularization. And you need to get a sense of sort of what kind of solutions k-means is able to find, right? And what are some of the issues, right? What kind of decision boundaries does it entail, etc. Okay, so k-means is our clustering, sort of most basic clustering problem, sort of as one instance of unsupervised learning, and the next one is dimension reduction, right? And so that's going to be the topic that's coming up, but in light of this, these issues here, I would propose that we actually stop here for today, and I'll try to fix this, and we'll continue just talking about dimension reduction in tomorrow's lecture. Okay, sorry again about this trouble. Okay, see you tomorrow.